In Chapter 20, we're going to be looking at electrochemistry. And the main part of electrochemistry, the main concept in electrochemistry is oxidation-reduction reactions. So we are going to look at the rules for oxidation-reduction reactions. Before we dig into the rules, though, I want to look at an example of an oxidation-reduction reaction. And we did talk about redox reactions, oxidation-reduction reactions back in Chapter 4. I did show you the rules at that point, or whoever your instructor was showed you the rules. And so here I want to go over the rules for oxidation-reduction reactions again, but let me just show you a really simple one. If you know that you have either a neutral element or a monatomic ion where you know what the charge is, then doing oxidation states is really easy. For example, this zinc is neutral, so it has an oxidation state of 0. This hydrogen has a +1 charge, so its oxidation state is +1. Zinc 2+ here has a charge of +2, so it has an oxidation state of +2. And then hydrogen here is neutral, so it has an oxidation state of 0. Now, there's a mnemonic that I like to use for oxidation-reduction reactions, and that mnemonic is oil rig. And oil rig, oxidation is losing electrons, and reduction is gaining electrons. So here we can see that zinc went from 0 to +2. That means it lost 2 electrons, so zinc got oxidized. Hydrogen went from +1 to 0. It gained an electron, so therefore hydrogen got reduced. So we can tell what is oxidized and what is reduced by looking at whatever gets more positive. That means it lost electrons, it got oxidized. And whatever gets more negative, for example, hydrogen here, it gains electrons and therefore it gets reduced. Now, one other thing, because I do want you to understand what the difference between oxidizing agent and reducing agent, and this may seem a little bit confusing, but it's really not too bad. Whatever is reduced, we call that the oxidizing agent. So here, since hydrogen plus got reduced, it is the oxidizing agent. It oxidizes the zinc. Whatever gets oxidized, that is going to be the reducing agent. So in this case, since zinc gets oxidized, zinc is going to reduce the hydrogen. So zinc is our reducing agent. All right, so we now want to look at rules for oxidation reduction, coming up with the oxidation states. So for the oxidation states, we're going to start off with the rules. You will notice that in the thing where I had your in-class assignment, there was a list there that is oxidation states, and it's got the rules for oxidation states. And I encourage you to print that out and have that next to your in-class assignment as you're going along and working on problems. And you'll see, in fact, here I'll just show you what this looks like. So here is the rules for oxidation states, and it's got what an oxidation state is, or oxidation number is another word for that, and then it's got these rules that I'm about to go through, and we will use those here in a moment. So for our first rule, if we have an element, so an element that doesn't have a charge on it, it's all by itself, then its oxidation state is going to be 0. And so, for example, chlorine, sodium, mercury, in that problem we just looked at, we had zinc and H2. Those were both elements, so they both had oxidation states of 0. If you have a monatomic ion, whatever the charge on that monatomic ion is, that's the oxidation state. So the oxidation state of an atom in a monatomic ion is the charge on the ion. So if you know for sure what the charge on an ion is, on a monatomic ion, then you know its oxidation state. So magnesium 2+, oxidation state of +2. Sodium +1, oxidation state of +1. Chloride, oxidation state of -1. So if we know that charge, then we know the oxidation state. Our third rule, and usually you'll follow these rules in order. You'll say, is it an element? No. Is there a monatomic ion present? Okay, yeah, if there is, then you put that in there, but if not, then you just move on to the next rule, and our next rule is oxygen. Oxygen, the oxidation state of oxygen, is -2 in most compounds. So, for example, in water, the calcium oxide, sodium oxide, we're actually going to look at those two here in just a few minutes. In all of these, the oxidation state of oxygen is -2. Now, there are some exceptions, and the exceptions include peroxides and superoxides. So if you've got a peroxide, like here is hydrogen peroxide, it's going to have an oxidation state of -1. And that's because oxygen has a bond to itself, and so it doesn't get to claim both of the electrons in that bond, so it ends up being -1. For superoxide, superoxides are fairly unusual. So you have a sodium that has a +1 charge, and then this O2 has a -1 charge. So that O2 has a -1 charge. That means the average charge on each of those oxygens is -1/2. So that means that the oxidation state is -1/2. That is very uncommon. It's almost always something in group 1, and it doesn't stick around very long usually. All right, so for our next rule, again, you'll go through these in order. Our next rule is going to be hydrogen. The oxidation state of hydrogen is +1, and that's going to be the case in most compounds. So here in all of these compounds, I'm not going to go through all of them. In all of these, it is a +1 oxidation state for hydrogen. The only time when it's not going to be, if it's in a compound, that it's not going to be +1 is if it is bonded to something that is less electronegative, and that usually means a metal. So, if hydrogen is bonded to something less electronegative, a metal, then it will have an oxidation state of -1. So like sodium hydride, and if you call something a hydride, it's -1 is the oxidation state of hydrogen. So calcium hydride, -1. Now to rule 5. When we have halogens, usually the oxidation state of a halogen is -1 if it's in a compound. However, that's not always the case for some of our halogens. For fluorine, there are no exceptions because the thing that determines oxidation state is going to be the electronegativity. Since fluorine is the meanest, baddest, most electronegative element on the whole periodic table, it always wins. It always has an oxidation state of -1, unless, of course, it's neutral, it's elemental fluorine. But if it's bonded to something, it's going to have an oxidation state of -1. All the other halogens are usually -1 if they're in binary compounds, but if they're bonded to something more electronegative, like a halogen above it or an oxygen, then we'll find that the oxidation state could be something different. And by something different, that means that we'll have to figure it out from context. So we will have to figure out the oxidation state from context. All right, so that's our 5th rule, hydrogen. The 6th rule, I call it add it up. And rule 6, it's all about making sure that the sum of all the oxidation states comes out to the total charge. So if we've got a compound, the sum of all the oxidation states in a neutral compound comes out to 0. The sum of all the oxidation states in a polyatomic ion comes out to the charge on that polyatomic ion. All right, now, if you're really familiar with this and you know how to do this, you can jump on and go to number 13. However, I am going to switch over to the names and oxidation states slideshow. And in the names and oxidation states slideshow, we're just going to practice a few of these. So we will practice a few of these. So I call it my supertastic oxidation number and compound name review. It's good for reviewing your compound names. And then one thing to help out here is instead of having this so that it takes up the whole screen, I'm going to put this here so that you can see the oxidation, the rules, those 6 rules for the oxidation state. In fact, I'm going to lower that down a little bit. All right, so our rules are element 0, monatomic ion, the charge, oxygen -2, hydrogen +1, halogens -1, and compound, and then added up is our last rule there. So I'm going to put that right there. So that is that document that I was showing you guys a little bit earlier, and then that way we can refer to that while we are looking at these. So let's look at the first one. Now, I make this also a naming review. I use this with my 1411 students. This, of course, is the element chlorine. So we just need to put chlorine. And so now, once we know what it is, we will identify, we'll go through the rules. Well, first, is this an element by itself? And the answer here is yes. So since that's an element, this has an oxidation state of 0. So we're done with that one. That one's pretty easy. So let's look at the next one. This is called calcium oxide. It is an ionic compound, and so that will help us answer the first question, is this an element by itself? And the answer is no, it's not an element by itself. We've got calcium and oxide. Question 2, is this a monatomic ion? And the answer is yes. We've got 2 monatomic ions that are present. We know for sure that that calcium, because calcium is in group 2, we know for sure that calcium, here it is, I'm getting my periodic table, there's calcium. Since calcium is in group 2, it's always going to have an oxidation state or a charge of +2. So we know that it is +2. Now, I want you to keep in mind, anytime you get past the point of, is this an element by itself? And if you answer no, then go ahead and figure out what the total charge on your thing is. If it's a neutral compound, the total charge is 0. If it's a polyatomic ion, then the total charge will be the polyatomic ion. Since this is a neutral compound, the total charge is 0. We just said that this has a monatomic ion in here, so calcium has a +2 charge, so the numbers up top are the oxidation states. We're going to take those oxidation states and multiply by the number of atoms. So +2 times 1 comes out to +2. All right, and then this is the hard part, and I'm putting that in air quotes. +2 plus some number gives us 0. Well, clearly that some number has to be -2. So we'll put a -2 there. And then when we're going up, we divide. So we're going to take -2 divided by 1 gives us -2. So the oxidation state on calcium is +2, and the oxidation state on oxygen is -2. Next, we want to look at oxidation. We want to look at this one. This one is called sodium oxide. So it is sodium oxide. We know it's not an element by itself, so we'll get the total charge. Since it's a neutral compound, the total charge comes out to 0. All right. And then we look, are there any monatomic ions present? In other words, are there any ions we know for sure what the charge is? And the answer is yeah. Sodium, and I'm going to bring my periodic table over here. Group 1, sodium is in group 1. That means it always has a charge of +1. So that means the sodium has to have a +1 oxidation state. We're now going to multiply. +1 times 2 gives us +2. +2 plus some number, it's got to be -2, right? It gives us 0, so this is -2. And then we'll take that -2 and divide by 1, or divide by the 1 oxygen to give us a -2. So the oxidation state of sodium is +1 and oxygen is -2. So far we haven't had any hard ones yet. All right, this is slightly more challenging because this is a polyatomic ion, and this, of course, is called nitrite. It is the nitrite ion. And we look at this, is this an element by itself? And if we answer no, which we're going to answer no, then that means that we need to look at the total charge. The charge on nitrite is -1. So over here, our total charge is equal to -1. So we'll have a -1 right there. All right, so now there are no monatomic ions. If this were called sodium nitrite, then yeah, we would have a monatomic ion, and we could label that sodium. But here we just have the nitrite by itself, so there are no monatomic ions. Next is oxygen present. Well, yeah, there's oxygen there. So if you get to this point and you haven't labeled oxygen, it's probably -2. So we'll have -2. -2 times 2 is -4. So some number plus -4 gives us -1. Well, that has to be +3. So we'll put a +3 there. So +3 and -4 gives us -1. We'll take that +3 and divide by the 1 nitrogen to give us a +3. So our oxidation state of nitrogen in nitrite is +3. Well, now let's look at nitrate. So here is nitrate. It's a polyatomic ion NO3-, that's nitrate. This is not an element by itself. There is not a monatomic ion present. And so we are going to put the total charge. The total charge here is -1. So we put a -1 right there. And then our next rule is oxygen present. Well, yes, it is. So oxygen is -2. We'll multiply -2 times 3. So -2 times 3 is -6. -6 plus some number gives us -1. That has to be +5. And then +5 divided by 1 gives us +5. So the oxidation state of nitrogen in nitrate is +5. Recall from the previous page that the oxidation state in nitrite was +3. Well, the nitrate, the nitrogen is more oxidized than the nitrite. And it's not a coincidence that there are 3 oxygens in nitrate, and it's more oxidized than in nitrite, where there are only 2 oxygens. So usually the more oxygen you have, the more oxidized it is. So let's look at the next one. Our next one here is lithium nitrite. So lithium nitrite is a neutral compound. And so since it's not an element by itself, it's a neutral compound, the total charge on a neutral compound, of course, is 0. So we'll put a 0 there. So now we want to look at our rules. It's not an element by itself. Is there a monatomic ion present? Well, yes, there is a monatomic ion. We know that lithium is in group 1. And again, I'm going to just scoot my periodic table over here. There's group 1. There's lithium right there in group 1. So we know that lithium has to have an oxidation state of +1. Since there's only one of them, we'll do 1 times 1 is 1. And since we have 2 elements left, we're going to go back to our list and keep following the rules until we're left with just one unmarked one. And so oxygen, yes, oxygen's there. And for oxygen, we're going to put -2. -2 times 2 gives us -4. So +1, -4, and some number gives us 0. Well, clearly that some number has to be +3. So we'll have a +3 oxidation state for nitrogen in lithium nitrite. And there we'll end up with a +3 on the nitrogen. Now, one thing that I want to point out is 2 slides ago when we did nitrite by itself, the oxidation state was +3. Here, when it's in a compound, it's +3. If you have the acid HNO2, nitrous acid, the nitrogen has an oxidation state of +3. So we'll find that when you've got a polyatomic ion, it doesn't matter if you have metals or hydrogens end up being attached to it, it's still going to have the same oxidation state. So the oxidation state here for nitrogen is +3. All right, let's look at this one. This one's called ammonium ion. It's a polyatomic ion, one of our few polyatomic cations. And it's not an element by itself, and there's no monatomic ion present. So we're going to put the total charge. Total charge here is +1, so we'll put a +1. That means the sum of all of our oxidation states has to come out to +1. We'll go through our list. Is oxygen present? No. Is hydrogen present? Yes. Since hydrogen is present, we're going to put a +1 up there. +1 times 4 gives us +4. And then some number plus positive 4 gives us positive 1. Well, that some number has to be negative 3. So negative 3, and since there's only one nitrogen here, we'll do negative 3 divided by 1 to give us negative 3. So the oxidation state of nitrogen in ammonium is negative 3, whereas in nitrate it was positive 5. So nitrogen has a very broad range of possible oxidation states. Next, we'll look at this one. This is called the phosphite ion, not to be confused with phosphate, its big brother, which has 4 oxygens. This one is phosphite with only 3 oxygens. So for phosphite, we'll look, is this an element by itself? No. Is there a monatomic ion present? No, this is just the polyatomic ion, so there's no monatomic ion present. Now, since it's not an element, I should have done this a second ago, the total charge, the sum of all the oxidation states, has to come out to that negative 3, so we'll put the negative 3 over here. There's not a monatomic ion present. Oxygen, well, yes, we do have oxygen, so that's negative 2. Negative 2 times 3 is negative 6. Some number plus negative 6 gives us negative 3. That sum number has to be positive 3. And then positive 3 divided by 1 gives us positive 3. So the phosphorus in phosphite ion has an oxidation state of positive 3. Next, sulfite. Sulfite, let's see, this is not an element by itself, so we look at the total charge. Our total charge here is negative 2, so we'll put that over here, meaning all of our oxidation states have to add up to negative 2. Is a monatomic ion present? No, there's not a monatomic ion present. Is oxygen present? Yes. So oxygen is negative 2. Negative 2 times 3 is negative 6. And then negative 6 plus some number gives us negative 2. Well, clearly that some number has to be positive 4. So we'll put a positive 4 there. We'll do positive 4 divided by 1, and that gives us positive 4. So the oxidation state of sulfur in sulfite is positive 4. So next, let's look at this one. This one is the bisulfite ion. We sometimes will call it the hydrogen sulfite ion. These are both acceptable names, but we'll see this is not an element by itself, so we'll need to get the total charge. Our total charge is right there, negative 1. The sum of our oxidation states needs to come out to that negative 1. Is there a monatomic ion present? No, there's no monatomic ion present. Is oxygen present? Yes. So here we'll put negative 2. Negative 2 times 3 is negative 6. Since we have 2 elements left, we're going to go back to our list and pick the next thing. Our next thing here is hydrogen. Well, hydrogen usually is positive 1. So positive 1 times 1 is positive 1. So positive 1, negative 6, and some number add up to give us negative 1. That some number has to be positive 4. So we'll put a positive 4 there, divide by 1, and we get positive 4. Well, just like we saw earlier with the nitrite and lithium nitrite, here sulfite, the sulfur had an oxidation state of plus 4, and in bisulfite, the oxidation state is plus 4. If we had sulfurous acid, which is H2SO3, it would also have an oxidation state of plus 4. And that's just kind of a handy trick to remember. Next, this is iodate. So this is the polyatomic ion iodate. This is, let's see, it's not an element by itself, so we're not going to have a 0 here. Our charge on iodate is negative 1, so we'll put a total charge of negative 1 right there. And then next, we will do, let's see, is there a monatomic ion present? No, there's no monatomic ion. Oxygen is present, so up here we're going to put negative 2. Negative 2 times 3 is negative 6. So some number plus negative 6 gives us negative 1. That some number clearly has to be positive 5. So positive 5 divided by 1 will give us positive 5. So the oxidation state of iodine in iodate is positive 5. All right, next. So this is the chromate ion. It is a polyatomic ion that has a metal in it. That chromium is part of the polyatomic ion, so that's something to remember here. So this is not an element by itself, so we need to look at the total charge. Our total charge is -2, so our sum of all our oxidation states will come out to -2. There is not a monatomic ion present, so this isn't sodium chromate or potassium chromate or anything. It's just chromate ion. So we'll go to the next rule, which is oxygen. Oxygen is -2. -2 times 4 is -8. So -8 plus some number gives us -2. Well, clearly that some number has to be +6. So +6 divided by 1 is +6. So the oxidation state of chromium in chromate is +6. All right, we're going to do one more of these. There are about 50 of these on this presentation, so I encourage you to. This will be in the. This will be on eCampus. You can go look at it. But we're going to do one more of them, and then we're going to switch over to the in-class assignment. So our last one here is Cr2O7 2-. This one is dichromate. So this is the dichromate ion. We'll see here that this is not an element by itself, and so we need to take whatever that charge is and put that over here as our total charge. So -2 is our total charge. There are no monatomic ions present. Typically, you'll get something like sodium dichromate or potassium dichromate. Those are common formulations with dichromate. And we will see here that there's no monatomic ion, so next we'll go to oxygen. So rule 3 is oxygen, -2. -2 times 7 is -14. Now, even though the numbers get a little big here, you don't want to stress out about this. You just want to follow the rules. Some number plus -14 gives us -2. Well, that some number clearly has to be +12. So +12. And now we want to divide. +12 divided by 1 will give us +6. All right. If you're having any trouble with these, I want you to go through and do more of them. However, we're going to stop and we're going to go to our in-class assignment problem. So here we're going to our in-class assignment problem. I'm going to move this out of the way. And we are going to assign the oxidation states on each of these. So in each of the following, identify the elements that undergo oxidation, a change in oxidation number, and indicate the magnitude of the change. So pretty much the best way to do this is just identify the oxidation state of each element and then figure out which things change. So for this one, we've got I2O5. It's a neutral compound. Oxygen comes out to -2. -2 times 5 is -10. So that means the iodine has to be +10. +10 divided by 2 is +5. And then here we've got carbon monoxide. The oxygen is -2. The carbon is +2. For iodine, that's neutral. So that is 0. And then for carbon dioxide, -2 for the oxygen and +4 for the carbon. So if we look at our 3 elements, the iodine, oxygen, and carbon, and look at how they change from reactant to product, all right, so iodine went from +5 to 0. Oxygen was -2 and stayed -2, and carbon went from +2 to +4. Well, so now we want to identify what is getting oxidized and what is getting reduced. The thing that is getting more positive is getting oxidized. So here we will say that the carbon is getting oxidized. All right, and then for the thing that is getting more negative, that's gaining electrons, is getting reduced. Since iodine is going from +5 to 0, it is getting reduced. And that's how we do that. All right, let's look at this next one. And on the next one here, Our charge on this, this is a monatomic ion. Our charge is 2 plus, so we'll put a +2 there for the oxidation state. All right, on this one, let's see, it's neutral compound, so the total thing comes out to 0. There's no oxygen, so hydrogen +1. +1 times 4 is +4. So this is -4. -4 divided by 2 is -2. So +1 and -2. For mercury here, it's neutral, 0. Nitrogen is 0. And then hydrogen here is +1. So now we'll look at each side. So we've got mercury, nitrogen, and hydrogen. And look at our reactant and product side. Mercury went from +2 to 0. Nitrogen went from -2 to 0. And hydrogen +1 to +1. So we would say that the mercury got more negative, so mercury got reduced. Sorry about, I didn't get enough room in there. And then nitrogen went from -2 to 0. It got more positive, so it got oxidized. All right, so mercury got reduced and nitrogen got oxidized. On the next one here, we've got H2S, so the hydrogen is +1, the sulfur ends up being -2. This hydrogen is +1. Nitrate, so -1, and if we work our way around, we'll get +5 for the nitrogen. Sulfur here is neutral, so it's 0. -2 for oxygen, +2 for the nitrogen, and then -2 for oxygen, +1 for the hydrogen. So on this one, let's see here. So we've got HSNO. I should make more room on the next version of this. Let's see, reactant, product. So hydrogen +1, +1, and then over here, hydrogen was +1. So hydrogen was +1 all the way through, so it's unchanged. Let's see. Sulfur, -2 to 0. So -2 to 0. Nitrogen went from +5 to +2. And then oxygen went from -2, it was -2 all the way. So -2, -2. So when we look, what got oxidized? And so the thing that got more positive was clearly the sulfur. So we'll say that sulfur was oxidized. I'm going to write it over here. So no, that's not a good idea. I'm going to put here oxidized. I'm just going to put ox. So sulfur was oxidized and nitrogen was reduced. So nitrogen was reduced. All right, finally on this last one, we've got sulfur dioxide. So -2 for the oxygen, +4 for sulfur. So here's nitric acid, -2, that's -6, +1, +5 for the nitrogen. Water, +1 for hydrogen and -2 for the oxygen. Here we've got sulfuric acid, -2 for the oxygen, +1 for the hydrogen. That gives us a +6 for the sulfur. And then here we've got -2 and +2 for the nitrogen. So again, I didn't leave enough room here. So let's kind of work our way through it. Sulfur, oxygen, hydrogen, and nitrogen. And then reactant. I'll put reactant, product. All right, so sulfur went from +4 to +6. Oxygen, so -2, -2, -2, negative is -2 all the way across. Hydrogen, +1, +1, it's +1 all the way across. And then nitrogen went from +5 to +2. So we'll say that sulfur was oxidized and nitrogen was reduced. All right. Well, that just about wraps up. Let me see. Make sure that wraps up this. Yes, that wraps up section 1. So chapter 20, section 1. And we're at 34 minutes here. So I'm going to stop this video and we'll start a new video for section 2.